I'm sorry, say it again?
For this equation,
Yeah.
how do we compare this data to this data from the original ascending?
This is your coefficients, right?
Yeah.
Right. So, and V naught is here, and half of acceleration is this, so you get your acceleration. Yeah, that's it. So, but you have a series of coefficients for the ascending and descending part.
Yeah.
Right.
So, but it would give us a series of you just say how different they are.
They are different.
So we
Yeah.
okay.
Yeah. So exam equation describe the position ascending and descending part, and be sure to include units. So which units these coefficients are, and then you're going to find A has unit of acceleration, B has unit of velocity.
So is that kind of what you got to the when we descending the acceleration was a little bit higher or no?
The descent
I mean, the
acceleration
descending was
I would expect to be the other way around. The descending should be less. The number should be less. Yeah. But don't just work on your data, and we can figure this out later. So now it's time to go to the board and start writing down your results for ascending acceleration and descending acceleration. And I'm taping because I would like the lab to be shown to my colleagues because they are using the lab as well. And we don't have. Yeah. The slope of position versus is the slope of velocity. I agree with this. Make sure your ruler is not 2 meters, it's 1 meter. The ruler is 1 meter. How are you doing? Oh, he wasn't lost? Yeah. Oh. Oh. Yeah, because here you have a bunch of right acceleration. Yeah. So you have 2 ways of assessing. This is the ascending part. This is your no, I see. This is when the ball comes out of the hand. The ball is in your hand right here. The ball is starting now. That is your descending part. So you have an ascending acceleration
That was the only homework question that I couldn't figure out what we just put on the slope.
Oh, okay.
Acceleration.
So you
And
got it?
she explained it to me today, this morning before class, and she showed me how to do it. I was trying to do it.
Okay, I need group 6, group 2 and group 3, and group 12. I need numbers. I need to be fed by numbers. Numbers.
But I think I got it, it's just a change in time on the phone. Yeah, over the velocity. If you look at it. That one, I'm having so much, like, I was trying to look at it. I don't know, you wanna write it in there? It's an x final minus x initial over time. Very smart, just. Something like, oh. I don't know about that one. Good morning, I remember now.
Group 6.
The bigger ones or the
Oh.
Eight.
Final position minus initial position. Over change. Which is the triangle.
Very good. Where's group 6? Group 6. Where's group 6? Oh, group 6?
Wait, yes.
Oh, 7? Oh,
We put ours under 5.
who's group 6? Group 12 is coming. Who's 6? Did I miss? Oh. Apparently we don't have a group 6. All right. Let's see if I can shoot to the graph. Okay. All right. Let me turn off. Turn this on. Okay, so here listing our ascending acceleration and our descending acceleration, and then by now, you guys, right in the beginning, we didn't advance much in the lab, but you should be able to understand you can get your acceleration either from the y position versus time graphic, which is the curved one, or you can also get your acceleration from the y velocity versus time graphic. Are we all there? Right? So the difference is in the curved one, you have to remember your acceleration has a dependency in time given by this expression. And logger pro gives the coefficient A, capital A, and so you have to make some correspondence with half of the acceleration. So your coefficient A that fits the curved data point is half of your acceleration. Are we all there? And when you go to the velocity versus time when you go to the velocity versus time or y velocity versus time graphic, the model is different. Y velocity is equal to nt plus b, where n is your acceleration. So again, the mantra we start singing last week is here repeated. The tangent to the graphic position versus time gives you velocity. The tangent or slope to the graphic velocity versus time gives you acceleration. Okay? And here are your points. Now, first of all, what can you say about the signs of your acceleration? I mean, in all data taking, the acceleration is always what?
Negative.
Negative. So what does it mean physically?
It's always a downward force.
You have, we haven't studied forces yet, but there is a downward force associated with the overall acceleration of your experiment, and is always pointing towards the origin, and you set the origin next to the ground. That's the first thing to note. The second thing to note is this. How does your acceleration vector, the sign of it, correspond to the sign of your velocity vector? And the velocity vector is the curve that I'm seeing most of you displaying now, is a straight line. So what can you say about the signs of velocity and acceleration in the ascending part of the curve? What is the sign of the velocity vector in the ascending part of the curve? Look at the graphic and tell me. The sign is what? Positive, negative, or what?
For velocity,
Yes.
it's negative.
What is the velocity in the ascending part of the graphic? Do not look at my face. I have a big nose. Look at your graphic, please. Is the velocity what? Positive or negative in the ascending part of the graphic?
Positive.
I heard positive, 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 and any other option? Positive. Any other option? Positive. So the velocity is positive in the ascending part. So ascending, you have a velocity that's positive, acceleration negative. When you have these two signs opposite to each other, what type of motion is? A speeding up motion or a slowing down motion? It's slowing down. And that's what happened, right? So you throw something up in the air, it slows down up to the point it stops, and then reverse back. In the descending part, what is the sign of your velocity vector? Just look in the graphic.
It's negative.
Negative. And what's the sign of your acceleration? Negative. The signs are the same. When the signs are the same, what does it mean? No, I need the word. Is it speeding up or is it slowing down? It's speeding up. So it's speeding up. So get out of the way. It's going to fall on you and hurt. Got it? When you compare these two data sets, just the magnitude, how big the number is. Which one, is there any trend when you compare these data with this data? I mean, look in general, like we did last week. So if you were to give some clever statement, right? Clever, something clever, and say, okay, I'm note something here.
Descending acceleration is bigger.
The descending acceleration is bigger than the ascending acceleration. You mean the number, right? When you drop the sign. So let's see if that is true. 9.4, 9.4 is the same. Here's 10 and 8, or 9. So descent is less. 9.7, 8.6, descent is less. 8.6, 7.6, descent is less. 9.9, 9.6, descent is less. 10.4, 9.5, descent is less. 8.7, 7.9, descent is less. 9.9, 8.4, descent is less. 9.96, 8.7, descent is less. 9.6, 8.6, descent is less. 8.4, 7.5, descent is less. So in all the data displayed here, the descending acceleration is less than the ascending acceleration, as far as absolute numbers concerned. Can you all got that? You agree with that? Okay. Why? Why? That's a $1 million question. We had something similar last week with a car going up the track. Going up the track, the acceleration was slightly bigger than going down the track. And you all said the problem was, the big guy was friction. So what's going on now? Air resistance, we call drag force. So there is a drag force, believe it or not, that levitates as it goes down, as we saw in the analysis in the beginning of the lab. As it goes down, so we have a force of gravity pulling down, but you have air resistance. And then this air resistance counterbalance gravity. In fact, when these skydivers, they drop off the airplane, they plunge down in such a way that drag force increases as increase their velocity. Their speed down, the speed goes up, the drag force goes up too, to the point that eventually the drag force matches up gravity force. And when this happened, you know what happened? The net force is zero. What happened with the skydiver? Here are the options. First, stop right there where it is. So it's plunging down. Now the drag force matches the gravity and stop. That's the first option. Second option, keep just speeding up. Third option, reverse back to the airplane. Fourth option, keeps going down with a constant velocity. Which option is more reasonable based on your experience of, how old are you in average? I would say 20, 28, 27, 25, 39, 42, 69, I don't know. So what happened? It stopped, right? So you go to the top of a building, you jump off the roof, and you plunge down, the drag force matches gravity. If you're lucky enough and you hit the floor, you stop right there, right? Certainly not. So net force, we are going to learn this stuff. So I'm just moving forward. So the net force, 0. And that implies constant what? Velocity. And implies also the acceleration of that system is 0. Okay. Good enough? Now, I didn't set up because we moved and I don't have things set up yet. But we can use a very precise way to measure the acceleration of gravity without air resistance. And I have all of these set. Next week I will show quickly. It's not a big deal. But if you ignore air and you do everything right, your scale is all right, the ball goes up and down, falls in the same spot it was thrown, there is no fallback, the acceleration measure is going to be some number that is going to be 9.81 meters per square second. Out of these groups here, which one was able to validate this number? How about group 1? How about group 2? It's group 2. How about group 3?
9.
Okay, I'm gonna do a check mark if you tell me which group kind of nail the data, which means as it goes up, the acceleration should be a number bigger than 9.81, which is the one due to acceleration, the force of acceleration alone. Since you have drag force, you add to that, right? So, and the descending part should be a number less than 9.81. So you tell me which of these groups were able to get and nail that information. Group 1,
No.
Group 2,
Yes. Yes.
Group 3,
No.
Group 4,
No.
Group 5,
Yes.
Group 6,
Yes. Oh. No, look at that.
Group 7,
Yes.
Group 8,
No.
Group 9,
Yes.
Group 10,
Yes. Yes.
11,
No.
12.
No.
So, so we have 2, 4, 5 groups, kind of less than half doing well, and other groups, the numbers were, consistent with the results. This is what we expect to get based on our previous analysis, but the numbers are less. Possible problems here. What do you think it is? Why the numbers are not there? See, the numbers seems to be always less, right? Not bigger, but less. This is good. This is less. Less than G, 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 less than G. Why do you think it is? Could be. If you have to go back to your data and redo it, what do you think would be the problem? Think about it. Because when you do your project, remember, you guys are going to do a project in the semester. You're going to go out, take data, bring it to the lab, and analyze. This is going to happen a lot. You're scaling. So the ruler, your set, the ball is supposed to go up and down and fall in the same spot. In most of the case, the ball was lifted in the proper place, but fall down behind where the camera was shooting. So the software, as it sees the ball going backward, falling behind the ruler, the scale changes. So the ruler becomes smaller or bigger than it is. So you have a problem with scaling and distances that it can't be fixed unless the ball falls exactly in the proper position. This is one possible mistake that's very common that might explain that. Okay? Another one is perhaps some airflow that is consistently flowing in that tunnel. So we were in a tunnel, right? So you could go there and analyze that too. But there are some consistency in the errors or discrepancies in our data. Good enough? Go get some lunch and shut down your computer.
You want us to answer all the questions on the web?
No. Just, by the way, no, I need to grade this, so make sure this is on my table.
But how far do you want us to go?
And I will give this back. No, right now you stop. I want you out of here.
Okay.
I love you all, but I want you out of here.
Okay, so just turn in whatever we have so far.
Yes, we are working together on this. So just put on my table, and I will return to you on Thursday during class.
How long is this acceleration? Well, what was the acceleration?